Hello and welcome to Anatomy and Physiology in Minecraft. My name is Daneray, y'all can call me Day. I have made a working neuron, or more accurately, a working axon in Minecraft, so we're gonna go over that today. Right now I'm priming the neuron. I used the Direwolf 2 mod pack from Feed the Beast. The actual actions themselves are made using mostly vanilla Minecraft Rails and combinations. I did find that I used Tinker's Construct, Railcraft, and Project Red mods more often than the rest, but you could use similar mods or mod packs to produce close to the same results. I mean, if you want to. If making neurons is something that interests you. Right now I'm going through this little rat way. These little rails down here are indicative of exocytosis. There was really no way for me to make exocytosis without using this. There was no way that I could just get the minecarts to just appear outside of the cell. So I chose this way. Plus, it gives us a nice visual of what happens. So I'm just going to go ahead and go through a couple more times to make sure that everything's running correctly. So the filled minecarts, or the minecarts with a loot chest in them, they are representative of neurotransmitters, and the empty minecarts are representative of calcium ions. Right now we're traveling along the length of the axon. You can see the myelin sheath, pretty much everything else. And here's where the signal is. So I went ahead and terminated the signal so the axon terminal would stop responding to me prepping it. Now the myelin sheath itself, this little glass blue layer that we just flew past, that's actually found only on axons, and what it does is it insulates the axon and increases the transmission speeds of the nerve impulses, which are the action potentials. It's just another name for action potential. Action potentials are only generated from cells with excitable membranes, like neurons, muscle cells, that sort of thing, and they're only generated in the axon itself. So when a neuron is adequately stimulated, it's going to generate that nerve impulse, and the stimulus will change the permeability of the neuron's membrane, and it will open specific voltage-gated channels on the axon. Now you'll see these little points. We'll go over and do a brief tour shortly of the neuron itself, but again, along the length, the arrow was pointing to the direction that the signal is flowing. So these spiny things, these spiny protrusions that you'll see off the cell body, are actually called dendrites. They receive input from other neurons. They are receptive regions themselves, but in this case I did make a presynaptic neuron, so this neuron will be delivering a signal. It's not receiving any signals to the dendrites at this point. So here's where our signal is. This is the axon hillock. That's where the axon joins the cell body. It's cone-like shape and produces a long, slender process. And the action potential is actually made right about here between the axon and the axon hillock, where they join. Axons themselves can be up to 1 meter long, or they can be incredibly short. But I went ahead and made a stationary axon terminal over here. You can see the white from the air. That's going to be our neurotransmitters. The little black dots are going to be our calcium ions. Receptive regions are the purple. The voltage-gated calcium channels are going to be the purple right there. I'm sorry, blue is the receptive regions. And green is the synapse vesicles. The two red dots in there are just mitochondria, and they really don't have much to do. I decided not to make a graded potential on the stationary one. It's just a little difficult to do. So here's a great aerial view of what we're going to be looking at today. And when we go over graded potential is essential to start a action potential. I'm not going to get into too much detail about that, but pretty much when the redstone lamps light up, that's the graded potential occurring. So here is a tour of our Axon terminal. Our mitochondrion is the lit red blocks. Synapse vesicle is these little green areas. Here's our voltage gated calcium channels. As you can see, they actually do have a gate in them. It's a little difficult to see, but they do have a real gate. Once they receive a signal from the end of the axon, then they will open and allow the minecarts that we're calling calcium ions to come in. So that's pretty cool. So none of this will happen until this axon will receive a input. Now here we're going over graded potential. See, the moment that our minecart hits our little blue space over here, goes over this detector rail, it's going to light up our redstone lamps, and that is a graded potential. Receptive points. I couldn't break the minecart. I had to break it, break the diamond. Sad face. Alright. Let's go start up the signal. Again, the little arrow that you see is pointing in the direction that the signal is going. Signals always travel away from the neuron cell body. They travel down the axon. So. I coded each redstone repeater to go every 4 ticks. So in a real cell, this would be instantaneous, but I wanted everybody to be able to see this, so I made the redstone receptors slow down the actual everything. Right now we see our calcium ions coming in, our neurotransmitters going out, finding the receptive points, and creating graded potential. Very quick, that's it. That's all it takes, which is fantastic. Right now, this is for the Minecraft people. This is my entire length of redstone. I put a repeater every few spaces, mainly because I'm paranoid. I know I can make it about 10 steps without doing a repeater, but I also wanted to slow down the signal enough, so I made lots of repeaters and set them all to 4 ticks. I wanted to slow down the actual signal enough to where we could get there in time. Back down. A couple things that I did want to mention is neurotransmitters actually, once they bind to the specific receptors, they actually get terminated by either reuptake through transport proteins, enzymatic degradation, or diffusion away from the membrane cell. I chose enzymatic degradation. Usually this occurs with lava, as you can see. Usually this occurs within the postsynaptic cleft. Fortunately, there was no way that I could do that without making it really, really messy, so I just chose to get rid of my neurotransmitters with lava in the postsynaptic neuron. Doesn't normally happen that way in real life. It happens within the cleft. So this is my neuron. If there are any other questions, anything that you guys want me to answer, like how I built it, or how does a axon work, please feel free to message me. Again, my name is Danery. Feel free to subscribe or watch my stream. Links are in the tab below. And have a good day, I guess. Alright, see you guys.